Yeah, thank you very much for the invitation. So today I will advertise a class of Liouville domains that I call polyhedral that I've been thinking about. I'll mention a bit later what the motivation for this construction is and some potential directions that can be explored from here, from this construction. So, okay, so the starting point for this construction is to have as input what I call polyhedral data. So it's really a pair of things. So let me set up some notation and sort of review this kind of combinatorics data that enters the construction for people that are have never seen things like toric geometry. So let's say that D is a positive integer, and we're working on a complex torus of dimension D, and that with coordinates Z1 through ZD. So what is polyhedral data? Well, it's the data of Fan sigma, and a Fan is a collection of convex cones in RD. So I drew a picture here. In this picture, you see an example where there are 7 cones, a 0-dimensional cone, 3 one-dimensional cones, and 3 two-dimensional cones. And what makes it a Fan is the fact that this collection is closed under taking faces of cones or taking intersections of cones. For example, if I take this 2-dimensional cone, this quadrant, its faces are these 2 rays, and they're also cones, 2 of the 7 cones in my collection. What I'm making 2 assumptions on the Fan. So the first is that whenever you see a cone, you can always write it as the convex solve of rays that are generated by some primitive lattice vectors that I'm denoting U rho. If rho is a ray, let's say rho 2 in this example, U rho 2 will be 0, 1. And the second assumption I want to make is that if you take the union of all the cones, you get the whole space, RD. Okay, and so this notion shows up in toric algebraic geometry. Essentially, this data is what you need to describe a way to compactify this complex torus you have, adding some divisor at infinity so that it becomes a compact variety, a proper toric variety. So a variety where the action extends to the compactification and it's somehow in the boundary at infinity, you see lower dimensional orbits of the complex torus action. Okay, the second piece of data that goes into this polyhedral data is the data of a piecewise linear function on the Fan. So what that means is a continuous function on RD with values in R, which is linear when restricted on each cone. And so I'm making these 2 assumptions. The first one is that if you take a cone of maximal dimension D, when you restrict one of these PL functions to the cone, you know it's gonna be the product by some vector in RD, but I'm assuming it's actually a lattice vector. That's an assumption. And the second assumption I'm making is that this PL function is actually strictly concave, meaning that you can present it as the minimum of these functionals that I described in the previous step. And there are no ties. So here is a picture to understand what that means. So you can sketch the graph of this function. Let's say it's a function on this Fan. So the graph will live in R3 now. And so along each cone, maximal cone is linear. So you see there's this kind of roof with 3 parts. And the assumption that it's strictly concave, it's basically the fact that whenever you cross a codimension 1 cone, then this roof bends. Okay, and in toric geometry, this data is what enters in specifying a Cartier divisor on the toric compactification. So whenever you have this data, an M-pole Cartier divisor. So whenever you have this data, you can construct a convex polytope. So it's the set of points that have product with each primitive generator array, which is greater or equal than phi, your PL function applied to the primitive generator. So it's a convex polytope, and its important feature is that its lattice points parameterize characters of the torus that are very special. So these characters are written as monomials in Z1 through ZD with exponents given by the coordinates of a lattice point. There are 10 in this example. And they're special because in algebraic geometry, you can think of them as a basis of sections for the line bundle associated to the divisor that phi describes. Okay, so the construction of the Liouville domains that I want to advertise today goes as follows. So first, you construct a global Liouville form on C star D by considering this function. It's log of the sum over all lattice points in the polytope delta of phi of norm squared of the corresponding character. And the first statement is that this function is pluri-subharmonic. So that means that it will define an exact symplectic structure, and this is a primitive for that structure, 1/2 DCF. So the second step of the construction is to consider a class of functions that I call polyhedral Hamiltonians. So they're defined as compositions of a smoothing function depending on some smoothing parameters epsilon, and the moment map for the action of the compact torus TD inside the complex torus C star D. So you might be worried that since I'm not, the toric variety associated to this data can be very singular, it doesn't maybe make sense to talk about, it's not really a symplectic toric manifold. It's not a manifold, but the usual formula for the moment map actually makes sense on this complex torus. So away from this divisor at infinity, and you can check it's still a moment map. So the smoothing function h epsilon, instead of writing what it is for now, so I'm just sketching its level sets in an example. So imagine your polytope delta phi is, let's say, the moment polytope of P2. Then the zero level set will be a smaller copy of this polytope. And as you increase the level sets, they will be smooth hypersurfaces. So they will be spheres. So it's kind of smoothings of the polyhedral boundary, and up to level 1, where they start becoming possibly non-compact, so with different topology. So the theorem is really that if here I changed notation, sorry, if I guess I called this phi earlier. So if phi is negative along the rays of the fan, then for any level set of this polyhedral Hamiltonians, and for epsilon small enough, then the level sets are hypersurfaces of contact type. And the second part of the statement is that there are families of one periodic form, so one periodic orbits of these Hamiltonians, 4 families that I denote BV epsilon, that are naturally associated with primitive lattice points in your fan. And if you call sigma B the smallest cone that contains such a lattice point, then its dimension determines the topology of this family. So it's a thickened copy of TD, thickened by a ball that has dimension D minus the dimension of this cone. So let me try to give an idea of what the motivation for this construction is. So in mirror symmetry, for Fano manifolds, we're interested in, starting from a Fano manifold X. So studying maybe, let's say, the quantum cohomology of X at Q equal 1. And a typical mirror symmetry statement in the closed string setting is to prove that this is maybe the ring of regular functions on the critical locus of some mirror function on a mirror variety X check. But it's actually hard to come up with examples of this kind of correspondence. But there is a general strategy to do that in the Fano case. So imagine your Fano degenerates in an algebraic family to a singular toric variety. And there are ways in algebraic geometry to construct these degenerations. So for example, a toric Q Fano. Then you can pick sigma to be the fan of this singular toric variety, and to pick your PL function to be along each ray equal to -r for r large enough. So this qualifies as polyhedral data in the sense I described above. And if you consider sub-level sets of the polyhedral Hamiltonians I just described, they give you Liouville domains in C star D that you can think of as, this green region here, the maximal torus orbit of this singular toric variety. And because this was the limit of a degeneration, you can flow symplectically this complex torus orbit to a symplectomorphic complex analytic set in your variety. And in particular, the moment fibers, these Lagrangian tori that live in C star D, they will flow to Lagrangian tori in this Liouville domain. And so the idea is that now, since we constructed a Liouville domain whose dynamics reflects the singularities of the boundary compactification, and it turns out that the central moment fiber is an exact Lagrangian torus in here, you can hope to study counts of holomorphic disks in this singular toric limit, which you can think of as deformations of actual holomorphic disks in the generic fiber of the degeneration. So you can study them, but it's not really rigorous because of the singularities. And so what you can hope to study instead are J-holomorphic half cylinders that you obtain by taking the symplectic completion of this Liouville domain and studying a Floer equation with Lagrangian boundary condition, these stars, and asymptotic condition, some Reb orbit in one of these families. So that's, and the idea is that more or less this should give you a local expression for this mirror function. So X check would be some gluing of complex tori, and W would be locally in each torus, some kind of count like this. Okay, so let me give you some more details on the construction. So I just sketched a picture for the smoothing function in a special case. In general, it's defined adapting ideas that have been introduced by Seidel in complex dimension 2, and MacLean generalized them in general dimension for complements of simple normal crossing divisors in smooth varieties. So here, morally, our divisor at infinity will be the toric divisor, but it's not simple normal crossing due to the singularities. And so we need some kind of cheap version of this technology that works in this setting. And I say cheap because we can use this torus symmetry at our advantage. So the smoothing functions I'm using are sums of bump functions applied to some radial coordinates. So the radial coordinates are defined by looking at the facets of this polytope. If you bring this to the left-hand side, you get some functions that are non-negative precisely on the interior of your polytope. So they give you a measure of distance from the facet, from each facet. And so if you call these radial functions R rho, and you apply to them certain bump functions, you get this kind of smoothing function that I was drawing. And these bump functions need to be chosen carefully so that the following then holds. And I can show you more pictures in question time. One key calculation you can do is that the flow, you can actually work out what the flow of these polyhedral Hamiltonians is very concretely. So it ends up being a sum of the Hamiltonian vector field is a sum of or a combination of Hamiltonian vector fields x u rho times derivatives of these bump functions. And these x u rhos are infinitesimal actions of one parameter subgroups of the stars. So in particular, they preserve each moment fiber. And another thing you can say is that if you look at these formulas for points that live in certain locally closed sets of your complex stars, then the formula localizes by taking only a sum over rays of the corresponding cones. So let me give you an idea of what these locally closed sets are. So basically, let's say the fan in this case is this cross with 4 quadrants. It's the fan of P1 cross P1. And you can imagine that each ray defines a region of C star D, which is the pre-image under the moment fiber of a little color around the corresponding facets of this polytube. And so these locally closed sets are obtained by taking for higher dimensional cones intersections of this kind of colors. So for example, this 2-dimensional cone would correspond to this little region here. Okay, so how do you prove that these hypersurfaces are contact type? So contact type really means that DH applied to the Liouville vector field needs to be positive. So this is theta, our Liouville form applied to XH, but thanks to the explicit formula for the flow you have, this is a sum of derivatives of these bump functions applied to times theta applied to infinitesimal actions of one parameter subgroups. And if you choose these bump functions carefully, these derivatives are negative. So this is the choice of bump functions I'm taking. And so all you need to show is that this pairing is negative, at least near infinity in the rho direction. And by that, I mean the following. So if you look back at what these smoothings look like, you'll see that if epsilon gets small enough, they get closer and closer to the polyhedral boundary at infinity somehow. And so since the union of these neighborhoods kind of is a neighborhood of infinity, all you need to show is that this is negative, at least if you're close to infinity in the rho there in each radial direction. And something you can check is that this action of the compact stars on the complex stars is actually more than just Hamiltonian. It's strictly exact. Okay, and so that upgrades the usual definition of Hamiltonian action to say that when you pair theta with an infinitesimal generator of the stars action, you get mu paired with u rho plus a constant that depends only on the ray. And the final step is to actually compute these constants. They end up being 0, but the calculation is actually one, I guess, the core technical step of the proof. And it relies, so I'm not going to describe it in any detail, but it relies on something that I call rapid averaging formula, which is basically an understanding of integrals of your one form over one parameter subgroups of these stars as pairings with your rho of certain quantities that are weighted averages of lattice points in the polytube. And the final step, once you have all this in place, is easy because so near infinity in the rho direction, this quantity is less than epsilon rho plus phi rho. And so you can make this less than 0 if epsilon is small enough. And I'll just conclude by saying, how do you produce families of periodic orbits? Well, Well, if you now have a lattice point in a cone, let's say in the interior, for example, of a two-dimensional cone in this picture, you can write it as a sum with rational coefficients of the primitive generators of its rays. And you can produce families of periodic orbits by imposing that the derivatives of these bank functions match negative the derivative negative minus these coefficients here. And if you do that, basically you're prescribing the flow of moment fibers of this action is linear, and of this Hamiltonian is linear, and you're basically prescribing a slope for families of moment fibers. And you can work out the periods of this, and they're very explicit, and that leads you to classify the one periodic orbits. So maybe I'll leave the tangential directions for possible questions. Thank you.
Thank you very much, Marco. Are there further questions? So Marco, maybe you can tell us about the tangential directions.
Yeah, so the motivation was for this construction was really mirror symmetry, as I said. But so this picture that I drew tells you that these Liouville domains that live somehow in these complex stars, they have symplectomorphic copies inside. They have symplectic embeddings in the original Fano. And so something you can hope to do, if you can say anything about any symplectic capacity of these Liouville domains, for example, and now we have this, I guess, I mean, the ones that I just looked at, I'm not an expert on the topic, but there are these rational SFT capacities, then, you know, by default, they will give you lower bounds for the same capacities of the Fano. And this holds, you know, in any dimension, and there are very general techniques to construct this degeneration. So I think it's a pretty flexible construction in this sense. And let me mention, there has been at least one result in this direction that doesn't use this construction. It's precedent to this work. But somehow uses the idea of toric degeneration to find lower bounds for capacities. Cave did find lower bounds for the Gromov width of very general projective varieties. And another direction is the study of toric singularities using symplectic homology. So you can ask, have some ongoing work where I proved that a partial toric resolution of singularities induces a symplectic exact symplectic embeddings of this kind of Liouville domains. And so you can gauge functoriality of symplectic homology to restrict the kind of resolution singularities that can exist. Maybe try to address some question in algebraic geometry by symplectic techniques. And I guess that's basically it. Something that maybe if there are no further questions, I can share also is a video. So these are the level sets of one of these polyhedral Hamiltonians. So this kind of game is meant to illustrate their dependence on the smoothing parameters. So the statement of the theorem I described is that over these level sets, you have the boundaries of your Liouville domains, and there are hypersurfaces of contact type in C star squared in this example.
Very, very interesting. Thank you.